Introduction to Algorithm Analysis. The topics of discussion today are: what are the factors considered for algorithm analysis? How do we analyze the efficiency of an algorithm? How do we analyze the time complexity of the algorithm? The comparison of growth of time complexity functions. What is the asymptotic notation, especially while studying in detail the big O notation? Factors considered for algorithm analysis. The three factors that are considered for algorithm analysis are the efficiency, the simplicity, and the generality. The efficiency of the algorithm is determined by the time efficiency and the space efficiency. The time efficiency of the algorithm is how fast the algorithm runs in a computer. The space efficiency of the algorithm depends on the program size and the data size and how much memory the algorithm uses in the computer. The simplicity of the algorithm is how much we are able to understand the algorithm and how easy the algorithm is able to be programmed. The generality of the problem the algorithm solves depends on the set of inputs it accepts. The algorithm efficiency can be analyzed by three cases. The first one, best case analysis. Second one, worst case analysis. And the third one is average case analysis. The best case analysis. It determines the fewer number of operations required to solve a problem for a given input n. Considering C of n as the count of operation for a sequential search, C best of n is equal to 1. That is, consider an array of n element and we are searching a element n naught. If n naught is present as the first element of the array, the number of comparison is 1. That is, when we compare the very first element with n naught, we find n naught in the first location of the array. Then the C best of n is equal to 1 for sequential search. So, what is worst case analysis? It determines the number of operations required to solve a problem for a given input n. So, for a sequential search, the value we are searching is at the last location of the array. That is, n naught is present at the nth location of the array. Then we have to make n comparisons to find n naught in the array. Hence, the C worst of n is equal to n. Average case analysis determines the average number of operations required to solve a problem for a given input n. Hence, C average of n is given as number of operations for each possibilities divided by the number of possibilities. Hence, for a sequential search, if the search element is present as the first element, the number of comparison done is 1. If the search element is the second element, hence the number of operation done will be 2. Similarly, for the third position, fourth position till the nth position, that is, for the search element to be present at the nth position, the number of comparisons will be n. So, the average case analysis is given as the number of operation for each possibilities, that is 1 plus 2 plus 2n divided by the number of possibilities, which is n. So, using the formula, we Deduce the C average of n as n plus 1 divided by 2 for a sequential search. How do we analyze the time complexity of an algorithm? To analyze the time complexity of an algorithm, we consider a model machine. The model machine is a single processor machine. The model machine executes the instruction sequentially. That is, one instruction is executed at a time followed by the subsequent instruction. The model machine uses 1 unit of time for arithmetic, logical, and assignment operations, and it also uses 1 unit of time for return from a function. Constant time complexity function. In constant time complexity function, the time complexity of the function does not depend on the value of the input. Here, consider the function sum, which gets the input A and B. It adds the two inputs A and B and returns the value. Here, the addition takes 1 unit of time as per the model machine, and the return statement takes 1 unit of time. Hence, the number of units of time for this function is 2. The time complexity of the function is also 2. Here, the time complexity does not depend on the value of the input. Hence, it is a constant time complexity function. Linear time complexity algorithm. In linear time complexity algorithm, the time complexity of the algorithm varies linearly over the input. For example, consider the function sum of list, which adds n elements of an array A. So let us see the units of time allocated to each statement in this function. In the assignment function, where 0 is assigned to total, it takes 1 unit of time. The for statement, which has the comparison and the assignment, has 2 units of time for each iteration. The assignment of total with one element of the array has 2 units of time for the addition and the assignment. The return has 1 unit of time. When you look at the table given here, which has the cost of the statement and the number of times the statement is executed, when we consider the first statement, that is the A statement, which assigns the value of 0 to total, the cost is 1 and the number of times the statement is executed is 1. The for loop takes 2 units of time for each iteration, and the number of times this for loop is executed is n plus 1. That is n true times and 1 false time, that is when the I value is incremented and it exceeds the value of n, that is the false time. The C statement, which is the total assignment statement, has 2 units of time for each iteration and it is executed n times. The return statement is executed 1 time. So, when you sum the number of times each statement is executed with the cost of the statement, you get the equation T sum of list. And when you simplify it, you get the value as 4n plus 4. This is a linear equation, and hence the time complexity of the sum of list is linear over the input n, that is the number of elements in the array A. Polynomial time complexity algorithm. In polynomial time complexity algorithm, the time complexity of the algorithm is represented as a polynomial equation of the input. For example, consider the function sum of matrix which adds each element of the matrix A. The size of the matrix is n cross n. That is, matrix A has n rows and n columns. Now let us see the units of time allocated for each statement in this function sum of matrix. The assignment of 0 to the variable sum takes 1 unit of time. The outer for loop with the I variable takes 2 units of time for the comparison and the assignment. The inner for loop with the j variable takes 2 units of time for the assignment and the comparison. The assignment statement, which assigns the sum of the variable sum and each element of the array A, takes 2 units of time for the addition and the assignment. The return statement has 1 unit of time. The table here gives the cost of the statement and the number of times the statement is executed. The first statement, assigning 0 to the variable sum, has a cost of 1 and the number of times the statement is executed is 1. The outer for loop has a cost of 2 and the number of times the statement is executed is n plus 1, very similar to our last example for n true cases and 1 false case. The inner for loop has 2 units of time for each iteration and the number of times the statement is executed is n multiplied by n plus 1. The n is for the outer for loop within which it is present. The n plus 1 is for the inner for loop where n is for the n true times and 1 is for the false time. The sum assignment statement has 2 units of time and it is executed n multiplied by n times for the outer and the inner for loop. The return statement is executed 1 time and its cost is 1. When you multiply the cost with the number of times the statement is executed and when you do the summation, it gives the time complexity of the entire algorithm, which is represented by T sum of matrix. And the equation is 4n squared plus 4n plus 4, which is a quadratic equation of the value n, where n is the dimension of the matrix. Logarithmic time complexity algorithm. In logarithmic time complexity algorithm, the time complexity of the algorithm varies as a logarithmic time of the input. For example, consider the piece of code given here. Here, every time the while loop is executed, the value of I is doubled and the while loop checks the value of I with the input value n. From the table given here, when n is equal to 8, the while loop is looped for 3 times. When n is equal to 16, the while loop is executed 4 times. When n is equal to 32, the while loop is executed 5 times. So, taking the log on the n value gives the number of times the while loop is executed. For example, 8 can be written as 2 cube. Hence, log 2 of 2 cube is equal to 3, which is the number of times the while loop is executed. Hence, the time complexity of the given piece of code is log 2 of n, hence the piece of code represents the logarithmic time complexity. The chart here represents the growth of time complexity of various algorithms. The x-axis of the chart represents the number of input n and the y-axis represents the time complexity function t. When you consider the line in the graph which is represented by 1, it is a constant time complexity function. Here, with the varying of n value, the t does not vary at all. Hence, the line is parallel to the x-axis. Similarly, the log n line varies slightly with the variation of n. When you see the line of n square, with the variation of n, the t values varies a little bit more steeply than the log n and n log n function. Hence, the n square time complexity algorithm varies its time in a steep manner when compared with the other algorithms which are represented by time complexity n, log n and 1. Asymptotic notations. Asymptotic notations are mathematical tools to represent the time complexity of the algorithm. Big O notation. It is one of the asymptotic notation and it is represented by capital letter O. The definition of big O notation is: a function t of n is said to be in big O of g of n denoted by t of n, an element of big O of g of n, if t of n is bounded above by some constant multiple of g of n for all large n. That is, if there exists some positive constant c and some non-negative integer n naught such that t of n is less than or equal to c multiplied by g of n for all n greater than or equal to n naught. For example, consider a function t of n equal to 3n squared plus 4n plus 2. We say this function t of n is a big O of another function g of n if there exists a constant c in which for a value of n greater than n naught always the t of n is less than or equal to c multiplied by g of n. That is, for this function we consider g of n is equal to n square. With that we construct the table. So here, when the value of n is equal to 1, t of n is equal to 9. G of n, which is c multiplied by n square, is 5. Similarly, for n is equal to 2, 3 and 4. But for n greater than or equal to 3, we always see that g of n is always greater than t of n. That is, n naught is equal to 3. We can always safely assume that the big O is the highest term in the time complexity function of the algorithm. Let us revisit the constant time complexity algorithm which we discussed previously. Here, the time complexity function is represented by T max is equal to 2. Hence, any algorithm with constant time complexity is represented as big O of 1. Similarly, let us revisit the linear time complexity algorithm. Here, the time complexity function T sum of list is represented by the expression 4n plus 4. Here, the maximum power of n in the expression is 1. Hence, here the big O of the linear time complexity algorithm is big O of n, with n having the maximum power of the expression that is represented as the time complexity function. Similarly, for polynomial time complexity algorithm, which is represented by the time complexity function T sum of matrix 4n squared plus 4n plus 4, the maximum power of n is 2. Hence, the big O of the polynomial time complexity algorithm is big O of n square, where 2 is the maximum power of the time complexity function that represents the algorithm. The big O of logarithmic time complexity algorithm is represented as big O of log n. Summarizing, in this presentation on Introduction to Algorithm Analysis, we discussed the various factors considered for algorithm analysis. How do we analyze the efficiency of an algorithm? The various time complexity functions of an algorithm, the comparison of the time complexity function and the asymptotic notation, especially the big O notation. Thank you.